this is a special topic on using topological models in searching for new crystal structures. And in some way, these models can supplement DFT models and USPEX algorithms. We have some experience in this field already, but these are some new, let's say, achievements in this field. I will present first some general information about topological description of crystal structures as nets. Then we will consider some topological relations using subnet and supernet concepts. And then the new network topological model of configuration space that helps us to find new structures, some methods of search for atomic configurations in solids using this model, and software and databases which can be used for this purpose, and some examples of application of this method. First, words about topological description of crystal structures. You know this very simple model which is used in crystal chemistry when we represent the structure as a periodic network with atoms and bones. And this is a bit, let's say, another model compared to typical physical model when we consider atomic nuclei and electron density around them. We can use this simple model also to algorithmize some standard operations for solid state transformations, and also to describe the structure with a simple set of numerical parameters. And these numerical parameters which characterize the topology, the connectivity of the structure, can be stored in databases. And now we have some special software which can create such databases, and then using these indices here, I present some typical set of such indices for types of topological indices which characterize the crystal structure up to isomorphism. And using these numbers, we can directly determine the topological type of the structure. And for this purpose, we use also our collection of topological types, which now includes more than 200,000 entries. Even more now, because we included many hypothetical structures, more than 500,000 hypothetical structures were added recently to this database. And to designate topology, we use some topological nomenclatures. One of such nomenclatures is shown here. This is our CSR. 3-letter codes. Using these codes, you can easily describe topological types shortly. An important background of the topological model is the subnet supernet concept. Actually, we can easily obtain subnet from some supernet by just breaking edges in this subnet. For example, if we have this initial topology, primitive cubic topology, we can break some bones like this here and get another very well-known topology, cadmium sulfate topology here. But this is, of course, not the only way to break the bones. We can do it in another way and get, for example, this two-fold interpenetrated arrays when we have two different, two actually topologically equivalent but anyway different networks which are not connected to each other, but interpenetrate to each other. For example, the third way gives us some low-dimensional structures from high-dimensional. So we have many methods to break bonds, and the question is, can we enumerate all of them? Within some restrictions, for example, if we restrict the topological complexity of the resulting networks, we can do it by strict algorithms. And this is actually what our software does also. Then using these relations between supernets and subnets, we can construct a so-called net relation graph that shows us these relations. And for example, if we have here this set of nets, and for example, B1, B2, and B3 nets are supernets with high connectivity, then we can break some bonds in them and produce from them some new nets, which are subnets in this case. And this is the net relation graph that shows us the relations between supernets and subnets. Then using this graph, we can find some important features of this system. For example, we can see that starting from some net, we can get many other nets. And if we take any pair of nets within the graph, we can find all possible ways of transformations of these nets by breaking bonds or creating new ones. So this is a way to enumerate possible topological transformations of the structure. Next point is that we can compute topological distance between these vertices, nets in the graph. For example, this net B4 has distance 1 to all other 4 nets in this part of the graph. This means that it can be transformed into these nets in one step by breaking just one kind of bond. But for example, the net B5 cannot be obtained from B4 because there are no topological ways between them, and the distance is formally infinite. So in this case, this graph consists of two isolated parts, and the corresponding networks are topologically independent. Now we can, for example, find also topologically fastest transformations between these nets. Again, for example, net B4 can be transformed to B7 in this way, but also in this way, the red one, which is the shortest one, of course, in this case. So we can expect that this way could be at least topologically favorable, most favorable. Now, one simple example for transition between diamond and Lonsdaleite structures. Here you see that one of possible topological ways of transformations of this structure structures is the intermediate 5-coordinated supernet, the transition state. And we can see here that if we break red bonds in diamond, this is just one kind of bond, the red bonds, then we create new yellow bonds in the transition state. We get finally Lonsdaleite. So diamond can be transformed to Lonsdaleite by breaking just one kind of bond and then creating one kind of new bonds. The transition state is still 3-dimensional, so this system does not require graphitization, passing from, for example, graphite subnet. Now let's consider the general concept of the network topological model. Let we have, for example, some configuration space with 4 different phases, A, B, C, and D. There are infinite number of geometrical configurations in this space, but we have just 4 different topological regions. This means that topologically we have just 4 points in this space, 4 different topologies. Although these topologies can be geometrically distorted, of course, but for our analysis it's not important, because we can work with abstract nets without their geometrical embedding. And this means that for this system, we just need to consider 4 points instead of infinite number. Of course, these boundaries between the regions can be complex, like this, like shown in this inset. And some intermediate topologies can exist in these regions. But anyway, the number of these topologies is limited. And we have here actually 4 so-called stable network regions and some metastable regions between them. And these metastable regions can be considered as topologically considered as supernets or subnets of the stable networks. And this also means that we can find possible transition pathways between known phases and also find new phases if needed. For example, let's phase B is diamond, and let phase A be Lonsdaleite. So this line, this pathway between them, topologically corresponds to the picture that I showed you before, and these intermediate phases can be, for example, 5 coordinated supernets. But what are the phases C and D here? We don't know, and probably these are new phases. For this purpose, to answer this question, we should find transition pathways to these phases from, let's say, Lonsdaleite or diamond, by again breaking or creating new bonds in them, and finally finding new intermediate states here. And we can scan in this way rather large, or probably even the whole rather large part, or even the whole configuration space, and enumerate all phases in this, all topologically different phases in this space. So importantly, the number of these phases is countable instead of a number of geometrical configurations. And this is also a way to study reconstructive phase transitions and single crystal to single crystal transformations and some solid state reactions, etc., etc. But these are simple structures. Diamond and Lonsdaleite are just monatomic structures. What to do with complex structures? For example, organic structures or metal organic coordination compounds, complex ionic, etc., etc. For this purpose, we can use the so-called underlying net concept when we simplify the complex structure and reduce it to some simple underlying net. An example I show you here is very well-known metal organic framework, one of actually the first metal organic framework synthesized in practice, MOF5. And this is the complete framework. This is the same for comparison. Then we find here the structural units, which are actually tetrahedral zinc complexes connected by organic links. And we consider these complexes and these links as the whole. We replace them with their centers of mass. And finally, after such simplification, we get the underlying topology, which is just a primitive cubic topology. Then we can consider topological transformations of this topology into other topologies. And these transformations will mimic the transformations of the complete structure. To construct the underlying net, we can use some strict simplification algorithms, which finally allow us to simplify quite different structures with different structural units, like, for example, atoms, organic or inorganic complex units, ligands, links, etc. And also metal clusters, polynuclear complex groups. For example, here in these three quite different fragments, we get the same topological fragment, simplified topological fragment. So probably these structures will be transformed in the same way, which will correspond to transformations of the underlying topology. And with this method, we can find relations, topological relations between quite different structures. Here, an example with two microporous structures is shown. This is on the left, this is sodalite, very well known zeolite, and on the right, the so-called ZIF, zinc imidazolite framework. They are different, of course, chemically, completely different, but topologically they are the same, actually. If we consider these fragments of in these two structures as the same fragment, we replace these imidazole ligands with their centers, which correspond to oxygen atoms in sodalite. We get the same sodalite underlying net. And after constructing underlying net, we can use the decoration operation to construct from this simple net some complex nets, complicated structures. Different methods of decoration give us different structures from the same initial topology. Also, of course, we can use this technique to consider structural transformations between complex structures. One more important point when we're looking for relations, topological relations between complex structures, is the local proximity of these structures, local, again, topological proximity. For example, we can consider, we can look in the databases for the structures which are locally similar to diamond structure. For this purpose, we can construct a rather large fragment of the diamond structure, like shown here, 41, for example, fragment, 41 atom fragment. This is the diamond structure, also a piece of diamond structure, and this is a fragment inside this structure. Okay, but then we can consider quite another topology like this, for example, more complicated, topologically more complicated than diamond. But anyway, this topology, this network contains these fragments, which are completely topologically the same. So we can say that this topology is locally quite similar to diamond, although if we consider the overall structure, it's different, of course. This search for final fragments inside the infinite structures is very powerful, and it for example, helps us to find the fragments which are responsible for topochemical reactions like these, or supramolecular synthons, which again correspond to some special methods of connecting structural units together. And this is also a way to find some typical supramolecular architectures in complex compounds. So this is quite unique possibility. For example, it is also useful for metals and intermetallic structures when you can find clusters, some metal clusters inside the bulky structure, inside the three-dimensional network. For this purpose, to perform the topological analysis, we use software which we developed since actually 1989, during last 30 years. This is ToposPro, and you can download this software for free at our website, topospro.com. And also now we started the project for online service which performs some operations realized in Topos also. And this is TopCrystal service. And with this service, you can use your CIF file and just drop this CIF file into this window, into this service. And you, after some time, you will get a complete topological analysis of your structure. For example, here, we consider calcite, and this service gives you two possible ways of topological consideration of this structure. When we consider atoms, carbon, calcium, and oxygen atoms as structural units, so when we consider the structure as a whole, or when we separate structural units more complicated, like carbonate ions and calcium atoms. And in this case, we have simpler topology. In this case, you see this is just PCU primitive cubic topology, like, for example, in MOF5, the same topology. So you can easily find all representations, all topological representations for your structure, and also find the possible topological relations with other structures. But for this purpose, you need to use topological databases. We produce a lot of different databases. I mentioned here just two our topological collections. The first collection is a so-called TTD collection, Topos Topological Databases. As I said already, it contains now hundreds of thousands of topologies, more than 6 actually, 100,000 now, including hypothetical structures. And all these data are arranged into in the Topos software, in the local version, and also in our online services. In TopCrystal, you can also find another set of collections. This is TTO collection, which shows us where these topologies are observed, in which structures. And now we have more than 2 million observations of these structures in real crystals or in some model structures. And again, in ToposPro, you can use this user interface and find the occurrences of the topologies and also the lists of the structures where these topologies are observed. And you can also use our online service, TopCrystal. In TopCrystal, after you, for example, determine the topology of your structure, you can immediately get the list of structures which have the same topology, and at least find first if your topology is new or not, and which structures have the same topologies. Probably these structures are quite similar to your structure. And directly from this service, you can go to Cambridge structural database or inorganic crystal structure database and see what is this structure, how it is constructed, etc., etc. So here all these services are integrated together. Now some more examples of application of all these methods and tools. Here again, see a simple example. This is the methods of how to get diamond and Lonsdaleite structures from graphite structure. We have graphite in the center, and the question is which atoms should be connected to each other to get diamond structure, or the Lonsdaleite structure. And the topological methods immediately give you this information, so you can see how the structure should be organized to get one topology or another topology. This is again diamond and Lonsdaleite, my old example, because they can be transformed to each other not through graphite, but also through three-dimensional structure without losing dimensionality. Okay. Now more complicated example, actually two examples. Here we have two pairs, tridymite and keatite. These are two silica polymorphs. Tridymite is high temperature polymorph, but at normal pressure. Keatite is high pressure polymorph. The same concerns ice, hexagonal ice, normal ice, let's say, and ice 3, which is high pressure phase of ice. Both these pairs, I mean tridymite and hexagonal ice, and also keatite and ice 3, have the same topology. This is Lonsdaleite topology, tridymite and ice hexagonal, and keatite and ice 3 has the keatite topology, some special topology, which is called keatite. And the question again, how to transform tridymite to keatite and vice versa, and also these two phases of ice. And here a possible topological way is shown when we, again, you see break yellow bones in the ice structure, in the hexagonal ice structure, then create new bones, red bones between water molecules. And finally, after relaxation, we get the structure of ice 3. This is quite complicated, actually, topologically complicated transformation. You see that the corresponding supernet is topologically quite complex. There are different nodes with different coordination in this supernet. And this transformation being quite complicated is of course hindered strongly, and it's quite it's actually impossible to get directly tridymite keatite from tridymite. There is no experimental way to find it, at least at the moment it's not it's unknown. Keatite can be obtained only from the melt by applying pressure. Between ice structures, this transition is possible, but at special conditions, and it's again not typical, let's say. It's very hindered anyway. So topological transformation also shows us the complexity of the transition. And this is energy profile for this transition for tridimide keatite. And you see here that there are many intermediate states here, many metastable topologies between these two structures. Again, it shows us how complicated is this transition. Another example, this is again two modifications of ice hexagonal and ice 2. Ice 2 can be obtained from hexagonal ice easily under pressure. And indeed, in this case, topological transition is quite simple. We have just one transition state between these two phases. But you see that the distances between the molecules, water molecules that should be connected to each other in a new phase in ice 2 is sometimes quite long. But anyway, from topological point of view, we need to break these yellow bones in ice hexagonal, then relax the structure, then form these new red bones, and finally get this right structure on the right. This is ice 2, and this is an intermediate supernet, the net before relaxation, the net after relaxation, which corresponds to the final structure. Another example concerns the structures which don't need the transformations, actually, which don't need the intermediate structure, intermediate topology. In this case, one topology can be transformed to another topology just by breaking bones or by creating new bones. No need to pass through the transition, topological transition state. For example, this typical transition, which occurs in some substances under high pressure, from zinc blende type to rock salt type, can be topologically described simply by breaking these red contacts in the initial rock salt structure, and the resulting network, although still geometrically similar to rock salt, but topologically it is already zinc blende. And after this, after some relaxation, you will get zinc blende. Vice versa, if we have geometrical configuration for zinc blende and the bones typical for zinc blende, but we create these new links, red links, the resulting topology will be equivalent to rock salt. And again, after relaxation, we will get rock salt as a result. So here there is no topological intermediate phase. Now, more about generating new crystal structures. Again, I talked already about graphite and obtaining diamond and lonsdaleite from graphite, but of course we can consider other ways of linking of graphite layers together, keeping typical four-fold connectivity for carbon atoms, and we will get new structures, new topologies, and these are new topologies which were not observed before. After relaxation, we get not bad structures with just 0.4 electron volt above diamond energy. And importantly, these structures are quite hard, close to diamond by hardness also. And in our recent study, not published yet, but submitted now, we generated many new carbon allotropes using the scheme in some way similar to evolutionary algorithms, but using the topological criteria for generation. So we started with some 6 initial structures, 6 initial carbon structures, known structures, and actually we selected them randomly. There were no, for example, diamond or lonsdaleite among these structures, but we were interested if we get diamond and lonsdaleite as offsprings of these parents. And we actually performed 3 steps. At each step, we generated some topological relatives using supernet subnet relations of the initial structures, and find at the first step 34 offsprings, topological offsprings. Then we select from these offsprings low energy structures, less than 0.2 electron volts compared to diamond, and created the next generation, the next set of parents, 5 new parents. From these parents, we generated another set of offsprings and repeated this procedure again. And at the third step, we obtained no parents, no low energy parents more. And finally, with all these steps, we get in total 224 new carbon allotropes. Among these allotropes, there are structures also close to diamond by energy, and also even one structure which are harder, a bit harder than diamond, but which has higher energy than diamond anyway. The details of this study will be, I hope, published soon. Okay, so if we consider all this scheme as a whole, the general algorithm is the following one. First, we consider some known structures which can be taken from different databases, like databases of real structures, real compounds, inorganic crystal structure database, Cambridge structural database, PDF database. Then we simplify them if needed to get simple underlying nets. Then we consider subnet, supernet relations between them and build the net relation graph for the resulting underlying net. And using, again, supernet, subnet relations, we can find topological transformations to get new phases from these known topologies. And if needed, these new phases can be then decorated with some complex structural units to get complicated structures. As a result, we can explore in detail the topological space instead of geometrical configuration space. And as I said already, for this purpose, we don't need to consider infinite number of configurations. Of course, these methods can be and should be, of course, combined with DFT approaches, and we did it already partially, also with Atom, within USPEX, when USPEX already can use some initial topological structures But of course, we need also DFT at each step of topological generation to check the stability of the structures and their properties, etc., etc. But the topological methods can help can help us to speed up the generation of the new structures, the method of to find the offsprings from the initial set of parent structures. So all these methods are united within our ToposPro software, also, as I said, in the local version and in partially, at least partially, in our online service. And in the end, I would like to thank my group in Samara Center for Theoretical Material Science, and also Russian Science Foundation for support, and you for your attention. Thank you.